Let us look at the other kinds of PLAs which are available apart from the ones which we discussed till yesterday's class. One is clocked PLAs. Clocked PLAs. You know that the PLA which you have discussed, they are not synchronous not for synchronous applications, synchronous logic applications. And if you want to make it clocked, then it is rather simple. Let us see. It is just a simple modification. Will give you a clocked PLA. Simple modification. So this is what is known as the clocked PLA. The only addition which we have made to the normal regular PLA or the folded PLA structure is this. The input signals are being fed through via switches which are driven by the clock phi 1, whereas output also, either the switch may be kept here or here, does not matter. The output also is taken, outputs are also taken via another set of switches driven by phi 2. This phi 1 and phi 2 are two-phase non-overlapping clocks. Phi 1 and phi 2 are two-phase non-overlapping clocks. So when phi 1 is high, these transistors are all on, but phi 2 is then off. Therefore, all these transistors remain off. Therefore, when the AND plane is activated, OR plane remains deactivated. It is not energized. So you make phi 1 on. The input signals are all transferred to the AND plane, and AND plane takes some time to stabilize the products. you know, that each product may take little bit different times to be formed, but here I am allowing that because phi 2 remains off for quite some time. When all the product terms are properly established, then phi 2 is high and phi 1 is instantaneously off. That is what is the thing. When phi 2 is high, phi 1 is 0 or off, and as a result the inputs, now you give some time for the inputs to come and get stabilized at the input nodes, and then you get the output from this. So exactly the same thing which you discussed in connection with the clock logic that I discussed for individual logic gates, but here this is for the whole array. So you just see, for converting a usual PLA to a clock PLA, you don't have to do much. Only thing is you have to add a series of transistor switches, or pass transistors, at the input as well as at the output, and then they have to be driven by two-phase non-overlapping clocks. So that is what is simply known as a clock PLA. Clock PLA is very important for, particularly for synchronous applications. Clock PLAs are used, but any asynchronous applications where very high speed, you know that if you can design like that, normal PLAs are used. Please see that. Otherwise, in most of the cases, perhaps clock PLAs are preferred. Most of the applications. This is one thing. The other kind of thing is called CMOS PLA or pseudo-NMOS. CMOS or pseudo-NMOS PLA. Now, what we do, you know that one drawback of PLA is that most of the operations, I should say, almost the entire operation is carried out by NMOSs. You remember, which are driver transistors, and only one load transistor is there per row or per column in the AND plane or OR plane respectively. And these load transistors in the conventional PLAs, NMOS PLAs, which I have discussed so far, they may be either a depletion mode device. In that case, the gate is connected to the source, or it may be an enhancement mode device with appropriate gate bias. If it is saturation, gate is connected to the drain. If it is linear region, gate is connected to a separate power supply VGG, which should be substantially higher than VDD. That you remember. But the problems in this enhancement mode load case, you already know that you have to maintain a very large beta ratio. The W/L ratio of all the driver transistors should be quite large, 10 times to 50 times, depending on the kind of transistor configuration. And that is how, in that case, the PLA will be unnecessarily big. Therefore, one prefers to use the other kind of NMOS where the load transistor is depletion mode transistor. In that case, we can use all NMOSs with W/L ratio which is only 4 to 5 times more than that of the load transistor, and as a result the PLA size is minimized. Okay, but the problem is that again, you know that so many NMOSs have to be used. Each of them should have a W/L ratio which is 4 to 5 times more than that of the load transistor. Therefore, the overall size again is quite large, and therefore there is a need for minimization. Can you just do something to minimize the area still further, apart from folding? Even after folding also, you see in that case, because you are maintaining that large, relatively large beta ratio of the transistors, you know that area, there is a problem so far as area is concerned. So can you do something to improve upon it? Then came the concept of CMOS PLA, but this is not really a CMOS in the sense that it really does not consume less power. That is why it is also called pseudo-NMOS PLA. What you do, simply you substitute the load transistors in N plane and OR plane by PMOS. all the load transistors, both in the AND plane. So load transistors and as well as OR planes are to be substituted by PMOSs. And all the gates of the PMOSs are returned to VSS. Gates connected to VSS, and VSS may be ground. And all the driver transistors in both planes and OR planes will remain as NMOSFETs. Remain as NMOSFETs. Only thing is the sources are returned to VSS, which may be ground also. You know, sometimes we keep VSS different potential for certain reasons, for DC level adjustment. Sometimes we do that. Say in ECL applications and other things, suppose I have to interface it. So for DC level, sometimes we may not, it is always not necessary that you keep VSS at 0 volt, but in most of the application, VSS is 0 and VDD is 5 volt and CMOS. So what you are really doing is, you are replacing all these transistors, which was earlier connected like this. You are replacing them simply by a PMOS. Now this one is connected to VSS. This is the simple only thing you do, nothing else. That means you have to form some N wells. In regular PLA structure, you have to form some N wells in left hand side as well as right hand top, left hand side as well as right hand top, sorry, the top side. And you have to form N wells, and into that, those N wells, you have to form all the load transistors. And only thing is, normally in ordinary CMOS technology, you know that the CMOS circuits, the gate is also connected to, gate of the load is also connected to the input, along with the gate of the driver transistors, but here gate is to be returned to VSS. Is it really a CMOS that way? Because this transistor, you are making such an arrangement that this is always on. So you are not keeping, just not like the ordinary conventional CMOS, that which is when one is on, the other is off kind of thing. You cannot do that here in this particular case. Therefore, that way, it is not, you are not getting the benefit of very, very low power consumption of CMOS, which is characteristic of CMOS in this particular kind of PLAs. Then why do you do that? This question should come to your mind. Because you know there will be a little bit higher area involved because you have to form N well. Fortunately, the N wells are only for the load transistors, which are very few in number. And you can all put them in a single N well. That is another advantage. You know that you see that for all these driver transistors, the drains are all connected and returned to ground, returned to VDD. So it is a very simple. Formation-wise, there is no problem. Technology-wise, layout-wise, there is no problem. There is a minimal increase of area so far as load transistors are concerned. But what about the driver transistors now? You remember, for a successful, this is not a dynamic operation. This is a static operation. Please remember, PLA is basic operation inside PLAs. A dynamic, not a simple static of operation, and therefore all the inverters involved are static inverters, and you have to maintain the so-called beta ratios or W/L ratios. What is the requirement for CMOS? In fact, for CMOS, the requirement is little bit on the just opposite side. That means the PMOSes should have a little bit higher W/L, around 2, compared to the NMOSes, in order that we get good performance from the DC level operations as well as noise margin points of view. And therefore, here what you have to do is all NMOSes may be kept quite small. Only the PMOSes, which are load transistors, their W/L ratios have to be made just roughly double that of the NMOSes. Therefore, what is ultimately happening? There is a drastic cut in area. Area will be highly reduced. Am I correct? Earlier case, you remember, the load for even kind of PLAs we have discussed, load transistors, if they had a W/L of 1/1, all the driver transistors had to maintain a W/L of 4/1. But in this case, what we are doing? All the driver transistors, if you maintain a ratio of 1/1, then the load transistor ratio will be simply 2:1, 2/1. And load transistors only few in number. But the bulk of operation is being carried out by the NMOSes. Therefore, there will be a tremendous reduction in area if you use the CMOS, so-called pseudo-NMOS. Though we call it CMOS, but it is not proper to call it CMOS. Why? You are not getting the benefit of low power consumption, low standby power consumption. That benefit you are not getting. That is why we call it pseudo-NMOS. It is NMOS, but we have added PMOS load, but it is always kept on. That's the difference between CMOS and this pseudo-NMOS. That here the PMOSes are being used as substitutes of the NMOS transistors, and they are kept always on. Only thing is, we don't have to bother much about the area, the W/L ratio, the area, the aspect ratio difference between the load and driver transistor. So this is the second kind of configuration, and this is also a very popular thing for ordinary PLA applications. But as you know that things are changing, people are trying to reduce power. PLAs are meant for realizing very large, combinational logic implementations. And in that case, we have to look for some alternative where the power consumption. You see the CMOS technology, even if you adopt, you cannot get the advantage of power consumption. So naturally, people prefer to go for the dynamic operation, dynamic CMOS. So that's the other thing is CMOS dynamic precharged PLA. This is very popular today. Let me explain it by giving a simple example. I'm drawing it. This is a very simple example. So this is a basic configuration. You see that what I have done, these are load transistors. Okay, these are load transistors. These are not really, should not be called the load transistors now. These are the transistors which are used for pre-charging the output node. In this case, these so-called the nodes from which the products emerge. So these load transistors are used, these so-called PMOSs are nothing but to precharge these node lines, the output, the product lines. Whereas these transistors which are connected to VSS, return to VSS, and again driven by the same clock phi 1, same clock phi 1, phi 1, phi 1. So when phi 1 is 0, these transistors are on and this transistor is off. So all the paths, the driver transistor paths are practically open circuit, and these product lines are charged, or we call it pre-charged, during which you are applying your inputs A, B, etc., which gets stabilized. And when phi 1 is 0, sorry, when phi 1 is 1, makes a transition from 0 to 1, these transistors turn off, And whatever things have happened here, what way the transistors are connected, this particular product lines will establish the corresponding signal, and that is what is known as evaluate phase. So we can actually, by making phi 1 0, you are producing the so-called, you are creating the so-called, it's called pre-charge phase, and turning phi 1 1, you are creating the situation which is called evaluate phase. And these are AND planes and OR planes are exactly similar. Only thing is they are driven by two clocks which are non-overlapping two-phase. Same thing. You can put your transistor. What are these things? These are nothing but a ground line, which I do. For example, I want a node, so what I do simply, I connect a transistor like this. I want a transistor here. So I will draw like this. Maybe I want a transistor here. And similarly, here I want to make some connections. For example, it may be like this. Depends on, because I have not started with any design, so it is up to you. Maybe at this point I have one. And so on and so forth. You remember that after I first introduced PLA, I gave a layout of the PLA in a stick diagram form. Remember, and there I showed the ground lines. Because I normally show that just a ground. I put that this end is grounded. But how to provide that ground? I have to make a distribution of that ground line, which is also shown in this diagram, because which has to be shown here, because I have to, all these so-called grounds are now floating. Floating means they are not directly grounded. They are grounded via a transistor. And that transistor is again driven by the same clock, phi 1. And exactly the same thing has been done here. You see that these are the load transistors. These are driven by the clock phi 2. And again, this transistor, which is in the pull out, pull down side. So this is nothing but pre-charge logic. This is, you have some pre-charge CMOS logic exactly was this. We had a PMOS up, NMOS down, intermediate, we had a block of NMOSs for producing the function f, and that which got inverted at the node, which is, therefore we got f bar at the output. But you remember the pre-charge logic, the problem of pre-charge logic was, pre-charge CMOS logic was when you want to cascade them. If you do not want to cascade them, there is no problem with ordinary pre-charge logic, pre-charge CMOS. So there is no question of cascading. So that problem, that so-called Domino CMOS concept, is not to be introduced here. Domino CMOS concept is not to be introduced. But suppose this same thing goes, suppose, I shall be discussing that afterward, there is another kind of PLA known as feedback reduced PLA, FRPLAs. Just like matrices, large matrices can be partitioned into small matrices and then manipulated for mathematical operations. Similarly, you can reduce the big PLA into smaller PLAs and cascade them for proper operation. This is, in fact, you have to apply some feedback loop also. That is why it is called feedback reduced PLAs. And then cascading question is coming. And then what has to be done? Then what has to be done? Inverters. Fortunately, inverters are already there. Fortunately, inverters are already there. So problem is not there. That is the advantage of, this particular configuration. And this is a very, of course, a very popular PLA now. Though we have studied the most, but in fact, the actual PLAs are mostly implemented by CMOS technology today and not by NMOS technology. And people use this dynamic approach as indicated here. So if I ask in the examination, draw, and that design a PLA, CMOS dynamic PLA, with folding, etc. You have to do all these things. Only thing is you have to finally draw the circuit like this. Suppose I ask you in the examination a question, design a PLA, CMOS dynamic PLA to implement the following functions F1, F2, etc., etc. Then you have to design exact and with folding, etc. The way I have discussed. You have to do all those things, but at the end, the circuit diagram has to be drawn like this, where these additional transistors have to be shown. But naturally, if I ask a question on this, I cannot give it on a very big one. You know that the drawback is so many ground line, etc. you have to show, and it may be difficult for you. So if I said somebody, not I, if anybody, in the question paper gives a problem on this, he has to give a little bit reduced problem, not a large problem for these kind of things. It is apparent. What is the advantage of this CMOS dynamic PLA in that case? Therefore, power consumption will be extremely reduced. And area ratio, no, you don't have to bother about area ratio. But only thing, the PMOSs have to be kept roughly double the area. W by L of PMOSs should be kept. Otherwise, no, the conductance of PMOS channels are really half of that of NMOS channel because of roughly half mobility of holes compared to electrons. So that should be kept in mind. But fortunately, PMOSs are very few in number. Entire operation is carried out by NMOSs. Therefore, the area point of view, it is very good. Power point of view, it is very good. And naturally, speed point of view also, it is quite good. But remember, this is not a static logic. This is a dynamic logic. And it does not matter. In most applications, static and dynamic logic are not at all important to it. Do you really use any logic at, say, 1 Hz or 5 Hz or 10 Hz? Rather, we just go for higher megahertz, even now gigahertz, gigabits per second kind of things. So dynamic is the concept of today, and not the static logic is the concept of today. But memory applications, there is still importance. Now, so far, we have discussed the PLA approach in a very conventional fashion. The same PLA approach we shall be using afterward for designing ROMs. MOS read-only memories we shall be discussing afterward. Okay? But there is another approach. This is also a PLA, but this is popularly called Vinwarger array. This is another PLA approach. This is also a programmable logic array. That is why it is called PLA, programmable logic array. But this is popularly because this is not the conventional PLA approach. And after the name of the main person behind him, Mr. Dr. Vinwarger, this name has been given Vinwarger array. And you shall see that this particular approach is more suitable when functions are available in a multi-level form, rather in terms of simple sum of products. For example, let us see this particular function, which is nothing but the carryout of an adder. So the carryout of an adder is simply, as you remember, is given by AB plus A B C I. Okay? So here what you have to do, you could really write it down in the form of sum of products, minimize and do the PLA. This is one approach, whatever already discussed. But in certain cases, this is not convenient, particularly from minimization point of view. It is better to perform first this exclusive OR operation. So exclusive OR and then and separately ANDing of A and B and ultimately summing them. Rather than doing all product operations first and summing them at the end, it may be convenient in certain applications that you form some big operations initially in stages. For example, as I said, you first do form A exclusive OR B. Then exactly normally the ways we draw a circuit, exactly that you first do this job, then do the product job, and separately you do this and then sum it up. And in that case, the simplistic way of drawing the block schematic of this is as simple. And normally, as you know, in MOS technology, NOR is simpler. NOR is most natural. Therefore, we shall try to realize everything via NOR. So you just do it. First, realize this one. So what you have to do, you take two NOR functions, two NOR gates. You apply A, B bar, A bar, B, then this one. Okay, it's very straightforward, and let us give the variant names for it. Number 1, number 2, 3, 4, 5, 6, 7. So you see that to realize this one, I had to use 7 NOR gates, and assuming that all the functions and their complements are available. That's we normally do. All the functions and their complements, inputs and their complements are available, and I am realizing this using 7 number of NOR functions, NOR gates, 2 input NOR gates. All right? This is a very simple example. You cannot say that I am not trying to justify that this is the optimum way of realizing this. Just to explain what Vinwarger array is, I have brought in this particular example. I think today I cannot go into the details of this Vinwarger configuration. I shall discuss in the next class. The approach is this, that you form, again, just like before, an array of transistors, an array of NMOS transistors to produce the so-called NOR operations with the load transistors on. How many load transistors will be required here? 7. 7 load transistors will be required. And how many NMOSes will be required? because these are all 2 inputs, excepting the last one. So double the number. That's the requirement. But I want to have a regular structure. I want to have a regular structure. So let me go, because of the shortage of time, I cannot go for discussing that. What I will request you is just try to do it yourself. That can you conceive any other alternative approach other than the standard PLA what I have discussed to realize this function, to realize this logic, this function through this logic scheme, not by any other scheme, in a regular fashion, in an array fashion, not by the conventional custom built approach, but an array, using an array. So you just do it yourself, try to do it. You can do it yourself, you can study book, and anything you can take help of book, but we shall discuss in the next class. Thank you.